Here's our first test for convergence or divergence of a series, where we decide on convergence or divergence without actually summing the series. If a series is convergent, the sum from 1 to infinity of an, then the limit as n goes to infinity of an must be 0. I'd like to warn you here that the converse is not true. We can easily have a series where the limit of the nth term as n goes to infinity is 0, but the series diverges. And for example, we've just looked at one, the sum from 1 to infinity of 1 over n, which was the harmonic series. Why is this true? Well, actually it's very simple to see that it's true. Notice that if a series is convergent, then we must have some number capital S, which is the sum of the series, and it's the limit as n goes to infinity of the partial sums. And notice also that the nth term is the nth partial sum minus the previous one, the n minus 1th partial sum. So the limit as n goes to infinity of the nth term is the limit as n goes to infinity of the nth partial sum minus the limit of the n minus 1th partial sums. But of course, both of these partial sums are heading towards the same number s, so that limit is s minus s, which is 0. So we're saying that if the series converges to finite sum, then the limit as n goes to infinity of the nth term has to be 0. And our test for divergence goes as follows. If the limit as n goes to infinity of an, the nth term of the series, is not 0, then we can immediately conclude that the series diverges. If the limit is 0, we cannot make any conclusion the series might converge or it might diverge. Well, let's apply this to a few series. Let's look at the sum from 1 to infinity of n squared plus 1 over 2n squared. Well, the limit as n goes to infinity of an is the limit as n goes to infinity of n squared plus 1 over 2n squared. I could replace the n by an x and calculate that limit as I do with rational functions. And that limit turns out to be the limit as n goes to infinity of 1 plus 1 over n squared over 2, which is 1/2. This is not 0, so according to my divergence test, I can immediately conclude that this series diverges. Well, let's try the second one, the sum from 1 to infinity of n squared plus 1 over 2n squared. And I'm going to apply this divergence test to see whether I can decide whether it converges or diverges. Notice the only conclusion I can make from my test is that the series either diverges or my test is inconclusive. I can never conclude convergence from this test. So I check the limit as n goes to infinity of the nth term. It's the limit as n goes to infinity of 1 plus 1 over n squared over 2n, and this is 0. And now the test is inconclusive. This series might be convergent or it might be divergent, but I have to admit at this point I don't know which one. Let's test the last one, the sum from 1 to infinity of n squared plus 1 over 2n. We take the limit as n goes to infinity of n squared plus 1 over 2n, the limit as n goes to infinity of the nth term. We see that that's actually infinity in this case, which is not 0, and I can conclude that this series diverges.